Okay, dear colleagues, so let's begin today's seminar. So our speaker today is Plamen Koshlukov from the State University of Campinas, and he will talk about the graded algebras that are sums of two homogeneous subalgebras. Please.
Thank you, Elitsa. And before starting, first I'd like to thank Professor Drensky and all the people from the Algebra and Logic section for this invitation. Yes, you see, I started here my career many, many years ago. And let us start with the talk. So this is joint work with Pedro Fagundes. And I'm going to start with some preliminaries. I consider algebras over a fixed field F. No need to suppose it infinite for now or in characteristic zero. Though later on I'll put some restrictions in some situations. But for now it's an arbitrary field. And I'll denote by F of X, the associative algebra, which is generated by some infinite sets, x1, x2, and so on. It is a countable set. And no need to assume unitary algebra for now. So the elements of this algebra are called the polynomials in these variables, non-commutative ones. And you can visualize it the following way. You form all the monomials on the set X, non-commutative monomial. That is, you suppose that they must words over this alphabet. And so you declare these monomials to be a basis of a vector space. That is, no linear combinations among them. And f of x will be then the vector space that has a basis as a basis all the monomials. Then a polynomial, okay, it should be this brackets, not so parentheses, but never mind. Will be a polynomial identity for some F algebra A. If F vanishes when you substitute the variables by arbitrary elements from the algebra. I will give some examples later on. If you take the set of all polynomial identities for A, then it forms an ideal in the free associative algebra. Since 0 times anything is 0, and then if you form linear combination of zeros, you get once again 0. In fact, it is a bit more than an ideal, since in addition to these two operations, that is forming linear combinations and multiplying from left or right by anything, it is invariant under substitutions. Since that is, it is invariant under endomorphisms of the free associative algebra. Since if you have an endomorphism, it is defined by the values of this, by the images under this endomorphism of the axis. This means that if you have an element F in the ideal of identities, then you have to substitute the axis by some polynomials from the free associative algebra. But when you substitute in A, you have polynomials, you substitute elements of A, you get another element of A. That's why it is closed under endomorphisms. And it's easy to see that the reverse is also true. That is, if you have an ideal in the free associative algebra, which is closed under endomorphisms, then it will be exactly the ideal of identities of a given algebra. Simply you take the quotient of the free associative algebra by this ideal. This is one of the possible constructions. And now some examples. Clearly, an algebra is commutative if and only if it satisfies this identity. Clearly, studying commutative algebra by means of polynomial identities is sort of stupid, since there are some other methods that work much better in the commutative case. But nevertheless, commutative algebras are PI algebras. That's algebras that satisfy polynomial identity. Then, take for example the upper triangular n by n matrices over F as an associative algebra. It satisfies this identity. The product of n commutators must be zero. Here, x1 commutator x2 is the usually bracket. That is x1, x2 minus x2, x1. This is easy to see since if you take A and B2 upper triangular matrices, then their commutator is an upper triangular matrix, but with zeros on the diagonal. But if you multiply n such matrices, you get zero, since they are strictly upper triangular. So it is immediate that this gives you zero. It's easy exercise. Then take 2 by 2 matrices over F as an associative algebra. It satisfies this identity, that is commutator squared commutes with everybody. Why? Take 2 n by n matrices, then their commutator is a traceless matrix. It is also an easy exercise in matrix calculus, in fact. And the only manner to prove it is by direct computation. But let us specialize for 2 by 2 matrices. The characteristic polynomial of a 2 by 2 matrix has this form. We know that every matrix vanishes its characteristic polynomial, but here I'll take C, a traceless matrix, that is a commutator. So this parcel becomes zero. Then you have that x squared is, if x is a traceless matrix, x squared will be a scalar matrix. That is minus the determinant of the matrix times the identity matrix. So this C square is traceless matrix, C square is a scalar matrix. And this gives you everything. Now, another important kind of a polynomial is the standard polynomial of degree n. It is simply you take x1 up to xn, the first n variables, make all the monomials of degree n on them, where are multilinear monomials. That is, every variable enters exactly once. And make the alternating sum. It has n factorial summands with the corresponding sign. Then it is clear that if A is of dimension n, then it will satisfy Sk for every k larger than n. Why? This is also elementary linear algebra. How we prove that if you have a determinant n by n matrix, and that the determinant is zero if the rows of the matrix, say, are linearly independent. It is more or less the same stuff. You take a basis for the algebra A. It has n elements. Then in Sk, you have k variables. K is larger than n. So when you substitute, the entries will be linearly independent. That gives you a very well-known theorem due to Mitsuru and Levitsky, I think 1951, plus minus 1. Gives us that the n by n matrices over a field F satisfy S2 times n, and moreover satisfies no identity of degree less than 2n. Not any identity of degree less than 2 times n. In fact, no need to assume F of field. You can take it any commutative unitary. This is much more difficult to prove. There are several proofs of it. The first one is the original due to a Mitsuri and Levitsky. It was combinatorial proof. Then Bertrand Constant gave another proof. In fact, he didn't know about the theorem when he proved his theorem. He had it as a note, this proof, but it was much more intricate. Then Sloan gave another proof for using graphs. People from group theory, when dealing with ring theory, use some other methods of graph theory. Then Razmistov, then Procesi gave another proof, and finally there was another proof by Rosset. Rosset was, I think, the last PhD student of Amitsur. And I don't think there will be other proofs, since Rosset proof fits on one page, even less in fact. And very nice, very elementary, very nice. It is simply a tricky problem for student Olympiad. Rather tricky, but very elementary. In fact, to prove that M2 satisfies S4, it is easy, since you can write S4 in this way, where this circle stands for the symmetric product, A times B plus B times A. So you can write S4 in this way. That is, you have products of two commutators. You take a basis of the vector space of M2, where you put as the first element the identity matrix, and then you choose the remaining three matrices arbitrarily in order to form a base. But if you substitute the identity matrix in a commutator, you get 0. So you cannot substitute the identity matrix. Since it is easy to see, then it is 0. But then you have only 3 matrices to substitute, and this is alternating in 4 variables. So the same argument as here shows you that S4 vanishes on M2. Okay, when n is larger than 2, as I told you here, it is much more difficult, but it is not our goal to discuss such things. In fact, if n equals to, the identities of n2 of f are rather well known. All the identities. In fact, it can be shown that the two identities we discussed, that commutator squared commutes with everybody plus S4, generates the ideal of identities of N2. This was shown in characteristic 0 by Razmistov. In fact, Razmistov found some finite list of 9 identities, if I'm not wrong, which could be reduced a bit. And then 1973, 1981, Drensky showed that, in fact, only these two are sufficient. And later on, it was shown that if f is infinite of positive characteristic larger than 3, then the same holds. If p equals 3, you have to add another identity, which in characteristic 0 larger than 3 is a consequence of the two identities we discussed, but in characteristic 3 5 would be a consequence. So you have to add it to get all the identities. But if f is infinite and the characteristic is 2, nobody knows whether the identities can be generated by a finite set or not. It is some nasty problem, but what to do? If n is larger than 2, it is much worse. The problem is widely open and wildly open, in fact. And my not very educated guess is that we simply lack the tools to, at least now. And now, a couple of examples on the contrary. Clearly, the free associative algebra, if X has at least 2 elements, satisfies no identities, since you cannot make any, you cannot produce any identity. an identity for this algebra means a linear combination among the basic elements, which is impossible, since the monomials form a basis. So f of x satisfies no identities at all. Another example. Take a vector space of infinite dimension. Then the algebra of linear transformations, all the endomorphisms of this space, it's an algebra we know, satisfies no polynomial identity. Why? Amițuru-Levitsky theorem gives an answer. For every n, you will have a subalgebra which is isomorphic to n by n matrix. But we know that n by n matrices satisfies no identity of degree less than 2 times n. So you make it for every n. And now, how you construct PI algebras if you have some collections of PI algebras? That is, you have some A sub I. You know that they are PI algebras, and you want to form some new PI algebra starting from this. Okay, the well-known theorem due to Birkhoff states that V is a variety of, okay, first, a variety of algebras means all algebras that satisfy some given system of identities. It might be algebras, it might be groups, anything. And a variety, V is a variety only if it is closed under subalgebras, factors, and direct products, possibly infinite. But this theorem is rather general, so as a very general result, you can hardly expect some concrete applications. First example is the following. Take A and B of PI, then their direct sum also satisfies polynomial identities. It is not difficult to see, since you can prove that. For example, if an algebra satisfies a polynomial identity, it must satisfy some multilinear polynomial identity. That is linear homogeneous. This means every variable participates in every monomial in degree 1, exactly. Then you take F an identity for A, G an identity for B, or multilinear on disjoint sets of variables, form their product. Then it is easy because of the direct sum, since A and B are ideals in C, and they multiply trivially, that this product will be an identity for C. But this construction is also on the trivial side. And another very non-trivial, rather non-trivial construction was given by Regev in 1972. Regev proved that if you have 2 PI algebras A and B over the field N, then their tensor product is also PI. And this theorem has very important consequences. One of them was obtained in the same paper by Regev, which says the following. You have a PI algebra, and suppose it satisfies some identity of degree D. Then, if you denote by Cn of A the codimension sequence of A, I will recall the definitions in the next one. Then these codimensions are bounded by D minus 1 to the 2 times n for every n. And the codimensions are defined in this way. It is in fact one of the most important numerical characteristics of T ideal. It measures how fast it grows. And let me start with it. Pn will be the span of all these multilinear monomials in the first n variables. It is a vector subspace here of dimension n factorial, of course, since you have n factorial permutations here. But if the characteristic of the field is zero, then it is known a T ideal is generated by its multilinear elements. So you can consider all these intersections if I is a T ideal in order to generate the T ideal. But Pn clearly is isomorphic to the left regular module of the symmetry group. The isomorphism is obvious. You map this monomial to C. Then, T ideals are invariant under endomorphisms, in particular under permutations of the variables. So, you have that this intersection here is a submodule, but then you can form the quotient. And it is also a module over the symmetry group. And I'll put Cn away to be, if A has a T ideal I, I'll put Cn to be the dimension of this vector space over this module. And then Regev's theorem is this. And the important point is that the dimension of Pn is n factorial. And if A is Pi, then this dimension must be less than or equal to some exponential function. Okay, exponential functions grow much slower than the factorial. And this is the important fact. This says in some informal language that this intersection fills all of the Pn when n is large. So it is sort of useless to study this intersection since it grows very much. Then it is better to study this quotient, which is smaller in a sense. Not to mention, you can apply the technique of representation theory of the symmetry group, which is quite well developed in characteristic zero. And now let us go to the main topics of the talk. I have an algebra A, which is a sum of two subalgebras. No need to consider direct sum, only a sum of two subalgebras. So, around 1960, Kegel proved that if B and C here are important as associative algebras, then so is A. In that same paper by Kegel, he proposed, but in some implicit form, that the following problem. If A satisfies polynomial identities, what conditions on B and C we can impose in order to guarantee that A satisfies the polynomial identity? And explicitly in 1994, Beidar and Mikhalev conjectured that if B and C both are Pi, then so is A. But let us recall if B and C are commutative, associative commutative algebras, this does not imply their sum A is commutative. It implies only that A will satisfy an identity of this kind. This was proved by Bakhturin and Jambrun the same year. That is not necessarily commutative, but it satisfies a very nice identity of the degree 4. Then in 2003, Felsenthal, he's a Brazilian, by the way, Jambrun and Leal, found various conditions on this subalgebras B and C that ensure the existence of a PI for the algebra A. 2001, Kępczyk and Puchilovsky of Poland, they proved that if B is PI and C is nil but a bounded index, that is satisfies an identity of the kind x to the n equals 0, then the algebra A is PI. Then Kępczyk and Puchilovsky also published a series of papers, some 6 or 7 papers, where they developed some kind of a structure theory for rings that are sums of two of their subrings. And finally, 2016, Kępczyk gave the positive answer to the question of Beidar and Mikhalev. In fact, he proved a bit more that you can consider this A, B, and C only rings. That is, A is a ring, which is a sum of two subrings B and C. B and C are PI. In this case, you assume the identities to have integer coefficients. As you consider the rings as algebras over the integers. And I'm going to deal with the analog of this problem for group graded algebras. Let me recall. You have a group G, an algebra, A will be G graded if you can decompose A as a direct sum of vectors of space AG, such that they multiply accordingly. That is, if you have two of these components multiplied, then you get some subspace, some subset of A, G times H. In fact, you can define gradients by monomids in the same way, multiplicative monomids. And let me give some example. Take an arbitrary group, an arbitrary algebra, and make the so-called trivial grading. That is, you concentrate everything on the neutral component and declare all the remaining components 0. This is trivial grading and does not contribute very much to our knowledge, but at least it exists. Another grading, take the polynomials in one variable over F. Take G as the infinite cyclic group and declare A to be the span of one-dimensional span of X to the N. It is the canonical grading on the polynomials by the degree. You can define the same for the polynomials in several variables as well, but I'm not going to discuss these gradients since they are well known and I don't need them back. Then take G the cyclic group of order n, A the n by n matrices, and declare the component of degree G to be the span of all matrix units whose indices I and J satisfy this congruence. I consider Z as additive group. That is, the main diagonal is the 0 component. Then you take the diagonal above the main diagonal as 1 component. You go on the diagonal above the main diagonal up to the end of the matrix, then switch to the last row, the first position. And so on, you repeat this to get the remaining components. Another construction is the following. Take G to be the direct product of two copies of Zn. A, once again, the n by n matrices. And let us suppose that is sort of a large field that is containing primitive nth root of 1. And I'll define two matrices, X and Y, in this way. The first diagonal matrix where you put the powers of W. And the second is once above the main diagonal, and the first entry of the last row as well. Okay, it's easy to see that x to the n is the identity, y to the n is also the identity, and x and y satisfy this rule of commutation. If G is an element of G, A and B, then you put A in it by G to be the span of one-dimensional span, x to the A, y to the B. Then this is indeed a grading because of this field. Moreover, take the group algebra of G. It is naturally graded by G. You simply declare the one-dimensional span of LG to be of degree G. And then the multiplication in G gives you that it is a grade. Another important example is the infinite dimensional Grassmann algebra, E. It is graded by Z2. And here you notice the center. U1 is the anti-commuting part. I'm going to define them explicitly in the next slide. And an associative algebra graded by Z2 is sometimes called a superalgebra. Okay, it is the for associative algebras, it is the same Z2 graded or superalgebra. But if A is not associative, then there are some other requirements. We'll explain them here. So, is the infinite dimensional Grassmann algebra of a vector space V, assuming it has a basis E1, E2, and so on. Then all these products, where the indices increase without repetitions, form a basis for E. Then E naught has a basis where here enter the monomials with even k and odd k for E1. And this is clearly as Z2 grading. Then you take Z2 graded algebra A. You define the Grassmann envelope of A in this way. And now, if you have a variety V, it might be the Lie or Jordan or whatever algebras, then an algebra A is called a V superalgebra if its Grassmann envelope belongs to V. So you can substitute V for commutative, Lie, Jordan, whatever. You get the notions of supercommutative, Lie super and Jordan superalgebras. Okay, they are seldom commutative or Lie or Jordan algebras, apart from the trivial cases. But at least they are extremely important in not only in mathematics, but also in theoretical physics. And now, vector subspace of G-graded algebra will be called graded or homogeneous. The usual definition, when it's a direct sum of its components. And in the same manner, you define a graded ideal, subalgebra, and so on. And now graded identities, you have once again a group G. And take the set X of the variables, split into several disjoint sets of infinite countable sets, which are indexed by G. And you form the free associative algebra the usual way. Okay, it will be graded in a natural way if you when you assume that X J, all its variables are of homogeneous degree G. Then extend this to the monomials. And this way, you get the free graded algebra. You know, this way, it is free in the usual sense, as in the ungraded case. And take a polynomial in it, then it will be a graded identity for a G-graded algebra A, whenever it vanishes for every evaluation that respects the grading. That is, if you have a variable of degree G, then you can substitute by L of degree G. But any substitution works. So an example, take 2 by 2 matrices with the standard Z gradient. It is on the diagonal. The main diagonal is 0 component. The second diagonal is 1 component. Then it satisfies and call Y the variables of degree 0, Z the variables of degree 1. Then it satisfies these two identities. See, a diagonal matrix is commute. The other, if you take two matrices of order 2 that have entries only on the second diagonal, then they satisfy this relation. And it can be shown, it is easy, that these two identities generate the idea of identities as long as it is infinite or even an integral domain. Now, why does one study graded identity? The first reason is probably the most logical, the curiosity. But seriously speaking, if an algebra is graded, you can study separated homogeneous components. And each of them will be smaller than the whole of the algebra. And most likely will be sort of simpler to study. Not to mention that when A is graded, you have some additional structure on the algebra, which also helps us understand its structure and so on and so on. And as an example, the identities for n by n matrices, as we already discussed, are known only for when n equals 1, trivial, n2. And we already discussed the identities for 2 by 2 matrices. But the generators are not known when n is larger than 3. On the other hand, if you consider the graded identities for Mn of F, you take the natural gradient we already discussed by Zn, then the graded identities are known. Well known and not that difficult to describe. In characteristics, in positive characteristics as well. Mn of F graded by some other groups, the graded identities are also known in some other situations. And our problem will be the following. You take an algebra, which is graded by a group, and assume B and C are subalgebras that are homogeneous in the grading, such that A is the sum of these subalgebras. So if B and C both satisfy some graded identities, we ask whether A still will satisfy them. That is the analogous for a problem due to Beidar and Mikhalev for graded algebras. And I'll start with some immediate facts. Take G a finite group. A is an algebra that is the sum of its homogeneous subalgebras. Suppose B and C satisfy some graded polynomial identity in neutral variables, that is only neutral variables. Then A is also a PI algebra, not only graded but PI algebra. And then A will satisfy graded identities as well. This is a direct consequence of a theorem due to Bahturin, Gembrun, and Regev, which relates the existence of a polynomial identity of a graded algebra if it satisfies some identity in degree 0, that is in the neutral component. But this is a direct consequence of this theorem. And another, which is a bit more difficult, is the following. Take G arbitrary, F arbitrary, and assume A is a class of G-graded algebras that is closed under graded homomorphic images. and under direct powers, including infinite ones. Let us assume further that graded prime algebras in A have, all of them have non-zero homogeneous ideals that satisfy some graded polynomial identity. That's for each graded prime algebra in A, you have non-zero homogeneous ideal that satisfies a graded polynomial identity. Then the whole class A consists of graded PI algebra. That is graded algebras that satisfy graded identity. Graded prime means that if you take two homogeneous ideals in A, if their product is zero, at least one of them is zero. Usual definition, but adapted to the graded case. And as a corollary, we have the following. Take a degraded algebra, which is a sum of B and C, where B is a homogeneous ideal non-zero, C is homogeneous subalgebra. Then if B and C satisfy graded identities, then A also satisfies a graded identity. And only to mention some idea of the proof, first, if A is not graded PI, then it can be shown that some direct power of A satisfies contains free-graded algebra as a homogeneous subalgebra. And then it can be proven, it is known for in the ungraded case, that if you take one-sided ideal of a free-graded algebra, then it's homogeneous, then it will not satisfy graded identity.
The wording of your statement sounds like there just exists some identity which is satisfied. Is this correct?
Yeah.
And it's not the case that all that is needed to characterize the algebra.
No, there exists. There exists
for any number of grades.
No, there exists.
Fine.
Now, a bit concerning semi-identities. I take A, which is the sum of B and C. Once again, in this situation, A is graded, B and C are homogeneous. Then clearly, for each G, you have this decomposition. And now I'll consider three variables corresponding to Bj, G, and Cj. In the following sense, if G is an element of our group, I consider Yg as a set of variables and Z another. Then take Y the union of this, disjunct union Z as well, and form the pre-graded algebra on Y union with Z. Now I'll set X G, the sum of these two, for every G in the group, and I'll denote by X this set. And I consider this subalgebra here. And the definition is the following. If I take a polynomial which depends on some Y's and some Z's, which are indexed by some element of the elements of the group, and I will call it a graded semi-identity for A, if it vanishes whenever I substitute all the Y's by elements in B, respecting the degrees, and all Z's by elements of C. That is, graded semi-identity is the following. It is graded, and some of the variables I can substitute by elements from one of the algebra, and the remaining from the other subalgebra. Okay, some of these graded semi-identities are called trivial, in the case where they are graded identities available. That is no matter how you substitute. They are okay. They are not trivial, but and to give an example, take the algebra without unit, and suppose S1 subalgebra, S2 ideal indeed. For example, the free associative algebra, non-unitary, take S1 as the subalgebra which is generated by all monomials not containing X1. And S2, the subalgebra which is generated by all the monomials that contain X1, then S2 will be Arrhenian. Put A 2 by 2 matrices of this form. D on the diagonal, S2 on the second diagonal. And then, as it to grading is given this way. First the main diagonal, second S2. Then A will be the sum of B and C, where B is of this form, C is of this form. Clearly they are homogeneous. And then you have a non-trivial graded semi-identity for A. Why? You see, 0 and 1, this corresponds to degree 1, but on B you have only zeros here to substitute. And now, a bit more about semi-identities. We form these sparse polynomials. Here is, you have some scalars, then you fix some of the letters, xd plus 1 up to x 2 times d minus 1. Put in between them the y's and permute all the y's. In fact, it extends sort of the notion of a sparse identity. And if you take this alpha sigma to be the sign of sigma, you get the well-known Capelli polynomials, because are quite important in PI theory. And now, another result in this direction, take once again, G graded, B and C homogeneous. Suppose that B satisfies some graded semi-identity of this form, of degree D1 here, where YG means some variable, some fixed degree G. And here it should be Z in fact, G minus 1. That is, all of them correspond to G minus degree G minus 1, here it is Z. And suppose that C1, the neutral component of C, satisfies some ordinary identity of degree D2. Then you can conclude that A satisfies a graded multilinear identity of degree N in homogeneous variables of degree G. Then N will be the least integer which is greater or equal to alpha, where alpha is this monster, or G is the order of the element G. Okay, I'm not going to enter into details about the proof since it is extensive. Combinatorial uses a combinatorial approach imitating the methods developed by Regev. And since it is too extensive, I'm going to skip it altogether. And now, in order to finish in a while, why to study all these results? Why one will bother with such partial results? And it might be better to try and prove a general theorem, Kępczyk style, in the graded case. Okay, it might be interesting, but first, Kępczyk theorem relies heavily on the structure theory of these rings that are sums of to subrings. In fact, well, the structure theory of associative algebra in the graded case is quite complete in the sense radicals, primitiveness, and so on and so on. It is quite well developed. But in the graded case, it is not as complete as in the ordinary case. And there are several striking differences in the structure of graded versus ordinary rings. For example, the basics, graded division rings. Okay, in the ungraded case, you know, this goes to Brouwer theory and so on and so on. It becomes complicated. But in the graded case, it is more complicated in the following sense. Take a G graded, it will be a graded division algebra if every homogeneous element is invertible, non-zero homogeneous element. Not that every element is invertible. For example, take the group algebra of G. It is graded division since every element of this kind, scalar times element of the group, is invertible, non-zero scalar. But it is not a division algebra if G is larger than 1. Moreover, that natural gradient on Mn by this abelian group, we already discussed the two matrices and forming their products. It is a division gradient since both matrices are invertible. But we know that in Mn we have a lot of matrices that are not invertible. Clearly, if you have a division algebra in the ordinary sense, then every grading unit will produce a graded division algebra. But there are much more. In fact, you can consider the following. Take some function from the direct product of G by itself to the non-zero scalars and twist the usual product in the group algebra defined in this way. G, new product by H will be G times H as in the group, but with this twist. F, of course, must satisfy some conditions in order to issue the associative. And then we also require that the neutral element in G behaves like 1. If you write it down, you get that F must be a 2 cosine on G. And in fact, in this way, you get the more general construction of graded division algebra. And okay, so it is quite complicated to study graded division algebra. There is a description, but it is much more intricate than in the ungraded case. And the most important reason in this one, Kępczyk theorem does not hold in the graded case. Why? Here is the example. Take a free associative algebra where X is an infinite countable set denoted by D, and take 2 by 2 matrices over D. Then take this grading on the diagonals, and I'll consider the following subalgebras. B will be this part, zeros here, that is upper triangular matrices, and C, lower triangular matrices. These are homogeneous. Clearly, A is the sum of this, but both of them, B and C, satisfy this identity. Variables of degree 1, 0, yield 0. Now, neither of these three algebras are PI, since all of them contain a copy of the free associative algebra. That is, they are not PI in the ordinary sense. And moreover, A satisfies no graded identities. It can be shown as well. It's easy. So we have the example and some corollaries. One might expect that the direct sum will behave better. No. The same example, but take it the first row and the second row of the matrix. And the same. The same two examples can be transferred easily to the gradedly case. That's the case of gradedly algebras, not superalgebras, but Z2 graded algebras. And some comments on it. I'm going to finish with this. Since you see, we produce some examples that involve monomial identity. That's some monomials that vanish. And as we already discussed, take Zn, take n by n matrices, the graded identities are known, and the proofs depend quite heavily on the fact that there are no monomial identities under this grading. Later on, DiVincenzo and Nardozza studied the graded identities for some very important algebras in PI theory, like n by n matrix over Grassmann, or these algebras I'm not going to discuss, and the results state more or less this way. The identities follow from some finite list of identities, modulo the monomial identities. In some particular cases, one can describe these monomial identities, but they are really very particular cases. And these monomial identities do not behave very smoothly. And here is a natural question, I do not know the answer. Let us suppose, once again, this A is a sum of two homogeneous subalgebras in the gradings. And let us suppose B and C satisfy some graded identities, but no monomial identities. Then maybe A will be graded PI. I do not know the answer, but it seems to me it might be affirmative. I don't know. And that's it.
Моето съзнание излиза и сега влизам в друго. Така че остана без обяд.
Добре. Чао. Чао. Okay. Only one last comment on the last slide. Some time ago, okay, I usually finish with thank you and благодаря for obvious reasons. My native language. A Russian guy in one of these talks told me, you see, but it is wrong. I told him that it was not wrong, since in Bulgarian it is exactly this way, and I was not going to write in Russian anyway.
Okay, do we have questions, comments? Let's see if there are questions on Zoom.
There's something similar if we have more than two summons. So
In the social
more
case,
general
no,
structure.
but I think there are some examples, not quite sure, but I think there are some conflicts in the ungraded case. When you have more than two summons. It seems that for two summons, it barely works.
Should be special.
But I'm not quite sure, in fact.
See. Are there questions?
No.
Okay, if not, then let's thank the speaker again. Okay, we can stop the recording.